All right. So, like they said, I'm going to give a talk today about getting started with Rust and WebAssembly in the browser today. Again, my name is Robert Mason. If you are interested, this is in blog form on the website listed there, which myself or someone else will post in the Slack at some point in the next 24 hours, probably. To just go over briefly what we're going to cover, we're going to do a crash course in Rust, how to write Hello World. We're going to break out Hello World into a library that might be usable from other Rust code. After that, we're going to just briefly cover what WebAssembly is. And then we're going to mash that stuff together and do Hello World in Rust, compile to WebAssembly, and then load it up in the browser and see how it works. Once we get through that, we'll take a short break so everybody can use the bathroom, and then we'll go into a more elaborate example, building a to-do application using WebAssembly in a little bit closer to real life thing. All right. So what is Rust? Rust is a programming language from Mozilla. It is strong, statically typed. It is fully compiled to native code with, so there's no virtual machine to have involved. There's no runtime libraries that you need to have. It's essentially a drop-in replacement for C or C++ code that you might be writing. That, when I first started out, it felt really intimidating to me. There are a lot of uses for it, and it's a great community. It's not as intimidating as you think. One thing that it provides that makes it unique is it gives you a memory safe guarantee. So you can't, in C and C++, you can have these null pointers or do all this crazy stuff that completely crash a program because they give you the freedom to do anything. This provides the guarantee that you won't do that and also doesn't have any kind of a garbage collector as overhead. So those are kind of the selling points on why you might be interested in using Rust. It is highly performant, much faster than you get in a lot of ways, and not a lot of overhead once you have something written. So to get started, there's two major tools you're going to interact with as a Rust developer. You have a question?
Could you make it a tad bigger?
Yes.
Yeah, that's good.
All right. Two major tools you're going to deal with when working with Rust. The first one is RustUp. The Rust compiler, a new version of it is published every 6 weeks. That's insanely fast for a language. And this tool helps to manage that in the easiest way possible. So that's going to be the primary way you deal with installing the Rust compiler and dealing with that piece. The other big tool is called Cargo. Cargo works a lot like NPM does for Node. It's going to manage your dependencies for the project you're using, does all the fetching and inclusion and linking and all the things you need there. It also will do installation of global modules. So if you need something available in the command line, you can use Cargo to install that there. So how do you do that? If you're on a Unix-like computer, so a Mac or Linux, you're going to use this really handy curl to rustup.rs and then run the file that comes down. If you're on a Windows computer, you're going to go to rustup.rs, and there will be an MSI to install RustUp, the Rust compiler, and Cargo. If you're interested in checking that everything is installed correctly, you can run these 3 commands, and you'll get back the version numbers that you've installed. All right. So now that we have all that stuff installed, how do you use it? Well, the first way you interact with Cargo is by using a cargo.toml file. If you're not familiar with toml, toml is essentially JSON, slightly different. It stands for Tom's Obvious Markup Language. Yeah, it's fun. But as you can see, it's key value pairs, and then it does a few other advanced things. But this is what a cargo.toml typically looks like. So you set your package stuff up in the package area. You can define your dependencies using semver if you're familiar with that. So these are the things that I need. You can actually do target-based dependencies. So if you need one thing on Windows or one thing on Mac, you can do that. And then any development dependencies. So it essentially works just like a package.json would work. Similarly, you can do cargo install from the command line to install a binary application that you might use from the shell. So those are the two major ways you're going to interact with Cargo. So let's build Hello World. So one of the really awesome things about Rust is when you type cargo new and then the name of a program, it will create a folder for you with that name. Inside it, it'll put the base dependency, the base file structure that you need. So you need a cargo.toml. It'll fill out anything it can, so the name of the package based on the folder you told it. And if you have Git credentials saved, it'll actually insert that into the author for you. It'll also create a source folder and the main.rs file. Main.rs is going to be the entry point for all Rust applications. So that's not idiomatic, that's a requirement for something that's compiled to be used. Similarly, the main.rs is going to have a main function, which is the main starting point for the application to run. And this is how it comes. We literally, just by typing cargo new hello world, we created a hello world application. This is the default main.rs that always gets created. So once we've done that, if we just type cargo run, it's going to compile that down for us into a binary, put it into our target folder. You can find it under target debug hello world, and then run it for us at the same time. So this is essentially the output we'll get is hello world. So we've done the first basic thing that everybody needs to do when learning a programming language, and we didn't have to write any code at all. So let's compartmentalize that a little bit. Let's pull it out and create a library. So similar to the main.rs as the requirement for a binary application that you're going to run, if you're going to build something that will be used by other applications, you put it in a lib.rs file. So to give you the anatomy, we've two functions here. Keyword pub means it's public, other people can use it. Keyword fn means it's a function. Then Rust idiomatically uses what they call snake case, which is all lowercase letters, underscores to separate words. And then just like C-style parameters. And then your type annotation for what you're going to return comes after a thin arrow, right? This might be something that you've seen similarly. Swift or a couple other languages use this syntax for return values. And then inside of that, the return value is implicit in Rust. If you've ever written Ruby, there's an implicit return value there as well. In Rust, it's the last statement in a function without a semicolon, right? So in this, generate greeting is going to return whatever generate custom greeting returns when you pass it the word world. So the second function, generate custom greeting, is going to take in a string. It's going to interpolate that into hello with an exclamation point after it and return that back. We know that because there's no semicolons there. That can be a little tough when you're getting started with Rust to remember the semicolon piece. They're not optional. In fact, they mean a lot. But once you really get into it, it starts to make things really nice, and it makes a lot of sense overall for the language design. So when we want to use that, we're going to use that, say, from our main.rs. So if we make these changes, so first we're going to put this first line that says extern crate hello world. That's going to say there's an external piece of code. I have it somewhere. It's either in my dependencies or it's in the file I live in. Bring that in and make it available for me. And then you import the actual pieces of it by using the use statement. So we're going to use hello world and then 2 colons to sort of get to the next level. And we'll just put our 2 function names there. Once we've done that, they're fully available. So we can put these 2 print statements here, generate greeting, which should say hello world, and then generate custom greeting with my name, because I wrote it, and that should say hello Robert. And so when we do cargo run, that should be the output. This is all pretty straightforward so far, not a lot of super interesting stuff. But that's kind of the crash course in how to write your first Rust program. What is Wasm? So Wasm, or WebAssembly, or Wasm, or however you want to say it, is a new standard for the browser. It is a code standard. It's based on a project called ASM.js, which is also from Mozilla. It is an intermediate language. So if you've ever written Java or C#, those are 2 languages that heavily rely on intermediate language in bytecode and the MSIL. It's essentially compiling to a halfway point that then can be more quickly compiled into native code and run slightly faster than if you're doing like Python interpretation. It's strong, statically typed. Right now, the only types allowed are floats and ints, both positive and negative for both, which makes things a little bit complicated. And it does not allow for a garbage collector currently, especially not the JavaScript garbage collector to pick up the pieces for us. So with all of that being said, Rust and WebAssembly kind of fit really well together. A lot of the same pieces in both of the lists. If you're not familiar with ASM.js, they have a website, asmjs.org. I encourage you to check it out. I also would highly encourage you to look up a talk from the PyCon 2014 called The Birth and Death of JavaScript. It sort of takes the ASM.js concept to another level and shows the true power of how fast this really can be. And WebAssembly is already faster than the iteration of ASM.js you see in that. So the question then is JavaScript dead or dying? No. Not anytime soon. The minimum viable product for WebAssembly was published 3 years ago this month. We have moved almost nowhere since then. Currently, everything about the community is about infrastructure from a community level, so building out the working groups to come up with the standards that will be the next iteration, and then stabilizing what already exists and stabilizing across browser implementations. That's where all the work is right now. If you go to the webassembly.org website, they have a really awesome roadmap, and all of these things say like they're work in progress, like they're actually doing this stuff. And the truth is they're actually writing the specs. Like someone has started writing this spec. Like nobody's implementing it. It's not even close to being implemented. And nothing on that list even remotely involves DOM manipulation. So JavaScript's going to be around for quite a while still. But there's definitely some opportunity to get some speed. So let's put this together. So if we're going to push together Rust and WebAssembly, one of the big things that we should talk about is, like I said before, WebAssembly only can know how to deal with integers and floats. So that becomes a big problem when you have a full language that can handle strings and arbitrary objects and things of that nature. You start to run into this problem where, like, say I want to return a string out of the function like we did before. Well, I need to know how long it is, and then I need to put it in a shared memory, and then I can return the pointer to where it starts in the shared memory, but then how do I tell the caller how long it is? Because I can only return one value. So you can see it's kind of a complicated scenario right now. It's super raw and super early. So there's a project out of Mozilla as well called Wasm BindGen. BindGen is a portmanteau of bindings and generation. It essentially will insert all of the Rust pieces that you need into your code to do that memory management, and also will generate a JavaScript file that you can use to import and then use all of those functions without having to deal with the pointers and the length and trying to decode from JavaScript strings to UTF-8 strings, which starts to get into a big mess. So this will make our lives a lot easier. So when we get started, the first thing that we're going to do is add a couple more pieces to our installation of Rust. The very first thing we want to do is install the nightly compiler. Since the compiler is on that really fast 6-week schedule, they like to have a part of it that's like not quite done, feature gated, and available for anyone to use and test and try things out. That's called the nightly compiler. So we're going to use rustup install nightly, and that will install a nightly version of the compiler. And then we're going to install the Wasm32 unknown target. So in compilers, there's typically this concept of target. It's fairly well used. The overall structure is the instruction set, followed by the manufacturer of the computer, followed by the OS. For us, we know it's going to be in Wasm. We don't know what kind of computer it's going to run on. We don't know who made the OS. So unknown sort of makes sense in that way if you conceptualize it. To do that, we're going to use rustup again. So rustup target add this Wasm32. And then just to be safe, we'll throw in that toolchain. So make sure that it's available for nightly, since that's where we're going to need to use it. And then the last thing we're going to do is this cargo install Wasm BindGen CLI. That's going to install globally for us a utility that will extract information from our WebAssembly module and build our JavaScript file for us. So all of those pieces kind of help make this process work. The other thing that we're going to need to do is make a couple of changes to our cargo.toml. First, we're going to need to add Wasm bindgen as a dependency so that we can use the things that it's going to do in our code. And the second thing is we're going to create a lib section. And in it, we're going to say what crate type it is. Crate is the term used for packages or libraries in Rust. So the crate type is CDYLIB, which is sort of a mashup of a C dynamic library. So it's a way for other types of languages to use Rust code exposed as though it was a C application, since it's such a widely used format. So once we do that in our lib.rs file, we do this first statement. These are the feature flags that we're going to turn on in the nightly compiler. They're the procedural macro, so proc macro. That's these annotations or attributes. If you're familiar with attributes in C# or decorators in TypeScript or Python, these act in a very similar way. Wasm custom section, that's going to be used to kind of transition information from one environment to another. And then the Wasm import module, and that'll allow us to import functions from the container scope. So it adds that section to our Wasm file. The extern crate Wasm bindgen statement, just like we did in our main.rs. And then we're going to use the prelude module from that. This is an idiom where a developer might put all of the useful things in the prelude module, re-export them there. So you can just do prelude star, and then you get all the stuff that's useful or they think is going to be most commonly used. Once we do that, we just annotate our two functions with the Wasm bindgen procedural macro, and that's it. We don't have to do anything else. We don't have to change the way our code looks. We don't have to do any pointer stuff, just that. At this point, we'll do cargo build. This time, we're going to put the +nightly flag in there. That's just a way to one-off use the nightly compiler if it's available. And then we'll say that the target is that Wasm32 target I talked about earlier. Once that's completed, then we'll run our Wasm bindgen CLI tool. That's going to extract that information and give us this wonderful JavaScript bindings file. So this is going to do all of the heavy lifting for getting from the WebAssembly environment where the Rust code lives to where our JavaScript code lives. Now you're going to see there's a lot of stuff in here. I'm not going to go through all of it because a lot of it is like really part of that minutia. The one thing that I just want to point out is you see here's generate greeting, right? So we have that function that's available and exported. And then we have down here generate custom greeting, right? So the two things we were hoping to export, we are actually exporting. So that's going to make all of this usable. All right. So now let's write a JavaScript file that can use that file. All right. So we'll use Webpack to do this. So we can do import. That's going to essentially resolve into a promise or be assigned to a promise. So we say mod.then, and then we get our Wasm module fully compiled and ready to go. And we assign that to our HW global variable. When we do that, we have it available for later. We're just going to register a click event on a button that will say hello. So it'll get the input from the DOM. If the input has a value, it'll go to the else statement. If it doesn't have a value, we'll just say hello world. We'll update the message with our generate greeting. That was the hello world version. If it does have a value, we'll pass that into generate custom greeting and then update the DOM. Update message is just going to get a container and shove an H1 in there with whatever text we tell it. So clear everything out and put it in there. So relatively simple. We're going to add Webpack. I chose to use Yarn here. You could use NPM. It doesn't really matter. Just to add Webpack, the CLI, and then Webpack dev server. You do need to be using Webpack 4 or greater to have WebAssembly module support. So that's just a little piece. And then in our Webpack config, it's pretty much as basic as you can get. We're really just pointing at our index.js file we just talked about and putting it into the dist folder. The last piece is just our HTML. So we just have the input, the button, and then the message container, and then our JavaScript. All right, so we run Webpack dev server and everything works. So let's take a look at the live demo. So here we go. This is the same HTML we were just looking at. If I click say hello, it says hello world. If I say hello JSMN. So now this is actually WebAssembly running in my browser right now. So it is absolutely possible to start with this today. All right. So that's the first part. So I know that was pretty fast. There's a lot of stuff in there. But that was just the beginning. So I think we're going to take a break. And then we'll come back for a slightly larger example that has a little bit more of a real world bent.
Yeah, awesome. Let's get a round of applause for our
Contrived example. So here's your specification. Remember, it's contrived. So the specification, the main goal is going to be to build a to-do list application. There's a server developer who's going to give you two routes, well, one route with two methods, to-dos. If you get on to-dos, you'll get the whole list of to-dos. If you post on it, you'll be modifying a file with a special message. We'll go over that later. The to-do object is going to look like this. ID, -1 for brand new, no real ID. Complete is the default for false, and then action is whatever string you provide. Here's your wireframe. This is what they want you to make it look like. So there's that. All right. So now the wrench in the works is that the server developer 2 months ago started writing Rust and refuses to do anything outside of Rust. They won't even send you JSON anymore. They'll only send you bin code, which is this binary serialization format based on the Rust memory model. So full fanboy right there. So how do we deal with that? We can use Wasm. Since Rust has the ability to serialize and deserialize JSON and serialize and deserialize bin code, we can create a library in Rust, compile it to WebAssembly, and use that in the browser to convert the messages we're getting from the server into JSON, which then can be consumed in our JavaScript environment. So to do that, we'll do cargo new. We're going to pass in this lib flag. That will make it create a library instead of a main.rs file. And then we'll call it bin code parser. And then we'll move into that folder. Once there, we're going to want to go ahead and update the package, or the cargo.toml, the package information. So in the library, we'll do that C dynamic library thing again. Moving down in our dependencies, we're going to use a few more dependencies. So the first one is called serde. That's ser for serialize, de for deserialize. It's a very strange mashup of the two, but it's where we are. Serde is kind of a blanket that provides sort of a framework that anyone doing serialization or deserialization should adhere to. And if you do that, then the users of your code get a bunch of stuff for free, and it's super nice. We're going to use the JSON implementation of that and the bin code implementation of that in those two down. And then we'll get our Wasm bindgen just like before. And then in the bottom here, I have these two statements of profile.release and profile.dev, where LTO, which stands for link time optimization, is turned on. This is just kind of a convenience. It will tree shake out anything we're not actually using that the Rust compiler might add. So it'll just keep our output a little bit smaller. All right. And what a nice guy. The server developer is willing to share their Rust models with you since you're writing Rust. So that's why in here, one of our dependencies is actually a path to these shared modules. So to go over what our models look like, we have our to-do. This first statement should look a lot like that JSON. Rust's primary object definition is called a struct. We define it by saying struct and then naming it. The convention for these is to use, what is that, Pascal case, so all caps starting. And then we define it by saying the ID is going to be an I32. In Rust, numbers need to have both type and size. So I for integer, U for unsigned integer, F for float, and then 32, 64, 128, 8, 16 standard numbers. Using I32 because that just seems fine. Bool for Boolean, so is it complete or not, and then the action string. When you define a struct, you only define the properties of that struct. You define any implementation details of it, any functions or methods, in an impl block or implementation block. So you say impl to do, and we'll create a constructor. Rust does not have a default constructor set up for it, but you can write static functions like this on a to-do, and we'll take in a string in this function, and then we'll assign that to the action and just set the ID to -1 and complete to false, because that's going to be our default. Notice that it's just kind of like a literal notation when you're constructing objects. Like that's really the way you construct them. This is just kind of a nice little convenience piece to put a function on it. All right. The next thing we're going to cover here is the enum, or enumeration. So if you've used TypeScript, or really most languages that are C-based, you've probably used an enum. Rust enums are slightly different. If you use Swift, Swift enums and Rust enums are very similar because you not only define the cases that are exclusive in your list, but you can also associate values with a particular case. So here we have our message enum. So the first one is getAll. That's just like a standard C-style enum. The next one is all, and that has, in parentheses around it, a type definition of to-do. And then if you're not familiar with generic notation, the angle brackets say that this is a thing that contains this type. Vec is the growable array type in Rust. So we have a vector of to-dos, right? A list of to-dos will be associated with our all case every time. All can't exist if there aren't to-dos associated with it. Similarly, adding a new to-do, we're going to need that to-do. Updating a to-do, we're going to need to know what the new to-do looks like. Removing a to-do, we'll just need the ID. So we just take the ID. And then if an error happens to occur, we'll just get a message in there. This is a really great way for a language as strict in type safety or static typing as Rust to do something dynamic. Like we're going to send a message over the wire on the internet. We're going to need a way to deal with what it looks like when it gets here. So this is kind of a nice little solution for that. Just to give you an example of how you can pull that data out, if we had a function and assume that there is a global data store that does stuff for us, we can define this function to do that takes in a message. And then we use the keyword match. That's going to be like a switch statement, essentially. So switch on the message. And each of the lines that have brackets in them is a case statement. So if it's a message get all, then we're just going to get all. Right? Remember, this is just an example, so it's not really doing anything. Right? We define that the case is ended with the fat arrow. And then we optionally can put those braces around it if we need multiple lines. And then the next one is the all message. So if that message is all, go to this code block and assign to-dos to the variable to-dos. So whatever value you have associated with you, I want it in the variable to-dos. So that's what we're saying here. In this, I'm just printing to-dos to the console. Similarly, we get one to-do here and one to-do here, and we get an ID here. And so we know that these are going to be the to-do objects or an ID, right? And then the last one would be the error case. In that case, we get a message. That message is going to be a string. So we can act on it that way, sort of pulling the data out as we're switching on that data. Another cool thing about Rust enums is enums are first-class citizens. So they can have impl blocks set up on them. So you can have functions and methods on enums, which make them even more powerful. So we have 3 functions defined on message right now. One of them, or the first one here, is going to be just a convenience constructor. Now, there's a lot we're going to break down here, and I'm going to try and go through it pretty quick because it could go really deep. So first, we're going to take a variable called data that implements a trait called into that can be that the target is string, essentially. Impl is a way to say, like, this value, I don't know what it's going to be, but it can be converted into a string. So long as it can be converted into a string, I'll take it. And then inside, I call .into, which will convert it into a string, because that's my target. Traits are like interfaces in TypeScript or C# or Java. If you've ever utilized an interface, they work a lot in the same way, or protocols in Swift. They work a lot in that same way. So what this is going to do, it's just going to take in something that can be converted into a string and put it into our error enum. One of the reasons that I do things like this is because Rust has a very strange model around strings. There's two types of strings. There's string literals that are stack allocated in memory, so they live like in a very strict place. And then there's heap allocated strings that can change size and do all of the things that like arrays can do and whatnot. Since that's the case, I don't want to force someone to give me a string so I can construct it. This allows me to give either a string or a string literal, or I don't know, a path, maybe, if that's the case. Anything that can be converted into a string. The nice thing is that this becomes like super cheap if it's a string. It doesn't do anything. You don't lose any performance on it. So that's kind of a brief overview of that. Next is 2 bytes. So this is the first like instance method we're going to see. Similar to Python, you'll see it takes the first argument as self. That means that it's going to be done on an instance of the message type. And this will return a vector of U8s, or just like a list of bytes. Like just a bunch of bytes is what's coming back. So we'll use this serialize function, and that's going to come from the Serde serialize library, right? So it's going to serialize it into bin code for us, self. So it's going to consume self and serialize it into bin code. And then technically serialization can fail, right? So we use this convenience method of unwrap. In this case, we're going to say unwrap or. So if it fails, we're just going to throw an empty vector back. The likelihood that this is going to ever happen is so slim that I feel OK with this contrived example doing this. If we move down to the from bytes, this is another constructor, convenience constructor that takes in bytes and attempts to serialize those bytes into an actual message enum in the Rust, like an actual message. This can fail, and this could fail inexplicably. Like we could just get garbage over the wire. Somebody could send something dumb or try to use this with the wrong data, and that would fail. So Rust uses this interesting idiom for error handling, and that's the result type. So it returns a result. That means whoever calls this needs to deal with it. Like, I'm going to tell you, this might fail. If it does, I don't know what you want to do, so I want you to decide that. So we use that match statement on deserialize because that also returns a result. And just if you want to take a peek, this is literally how result is defined in the Rust standard library, is result with type T and type E. And then the enum cases are OK with type T and error with type E. So when I say I am going to return you a result with a type of message, if it's OK, or string, if it fails, then that's essentially what fills in the T and E in those situations. So in our actual function definition, we'll attempt to deserialize it using that match statement. If we hit the OK case, then we know we have a message, right? It worked. So we'll return back OK with that message in there. If it failed, then we'll shove whatever the error message is into a string and return that back as the error case. So whoever's calling this can then deal with whatever error might have happened, print it to the console, or crash, or try again, or whatever it is that you wanted to do. So that's kind of like the overall models we're going to be working with. Now let's actually dig into the library we're going to create. So the first line should look familiar. We're just going to add those compiler flags to say we're going to use this stuff. We then declare our external crate dependencies. So this is that list, literally the same list from when we were in the cargo.toml. Then we're going to use the prelude like before, and then we're also going to add the extern crate for Wasm tutorial shared. That's going to be where the shared models are going to live. So that's that local path I pointed out at the end. Last, we're going to use those, Specifically in the models, we're going to use the message and to-do, the two items that we've gone over. All right, so now let's get to writing some actual code, not just importing stuff. The first thing I like to do, at least when I'm debugging, is create an extern block. Extern is a way to say that I'm going to bring something in from somewhere else. It'll most likely fit the C binary requirements. Here, we're actually defining console.log. So I'm going to be able, from this module, to write to the browser's console. We're going to use Wasm bindgen to help us with that. So first, we mark the extern block with Wasm bindgen. Then we mark our function. And we're just going to define kind of like the shape of the function, not any implementation, and give it this sort of clue here. The JS namespace is going to be console. In this situation, we're just going to take one string. Console.log is variadic, or however you say that. So you could make this a list of them. But with the way Rust works, we have to decide. So in this situation, I just went with one string, right? So now the heavy lifting for our all messages is going to come into bin code to JSON. So we're going to get in these random bytes that are going to represent a list of Rust structs, or essentially a Rust message, enum. And we're going to need to turn that into a list of to-dos in JSON. So to do that, we're going to take in that buffer, which is a vector of 8-bit integers, right? Unsigned 8-bit integers. We're going to use this. This is the other way you can deal with enums in Rust. I'm going to say if let, OK, that's our enum case. If it's OK, assign it to message. So it's a lot of that same syntax from match. And then I'm going to call the from bytes constructor on my message. If it doesn't work, I don't really care at this point, because it's just kind of a contrived example, right? If I get a message, so if that works out, I'm going to match on that and make sure I have the all case, right? I have the all message, or the error message, right? One of those two is going to be coming from the server to me. So I'm going to need to deal with those two. The other 5 or so cases, that's going to be handled somewhere else. So I can use this underscore, this last case that's an underscore. That's the catch-all or default case if you were using a switch, right? So if I get an all, I'm going to if let OK for that serialization, right? So I have a list of to-dos. I'm going to turn it into a JSON string. And then I'm going to return early from this function with that string, right? Returns are normally implicit unless you're escaping early in this situation. You can absolutely, if you wanted to, you could write returns explicitly in all of your functions. But this is more of an idiomatic way to do things in Rust. If we hit the error, I want to console log the error. If we hit the default case, I don't know what you wanted me to do. So I'm just going to print that it's the incorrect type to the console. In the event that we don't pass these if-lets and matches, we're going to hit this bottom situation, which will return a string that's just an empty JavaScript array, right? So basic structure, we're pulling out the message, grabbing the to-dos out of it, turning that into JSON, and sending it back. The other pieces we're going to need to do is we're going to need to make messages to send back to the server, right? So to do that, we're going to have these functions take in the specific parts of a to-do, and then turn that into a Rust to-do, put it in a message, and then serialize it using that 2 bytes function that we defined, and send that back as a bunch of bytes. So we essentially do the same thing in all 4 of these different messages, right? Annotating them with that Wasm bindgen procedural macro so that we'll get all of the glue and special stuff that we'll need to make this work in the browser. Right? Does that make sense, mostly? So to build this, we'll do that same cargo plus nightly build, and then the target, and then run our Wasm bindgen CLI tool against that to pull that information out and create our bindings. Now we have our bindings file again. Now when I wrote this, Webpack and Chrome had this really interesting problem. So Chrome has decided that any WebAssembly modules greater than 4 kilobytes cannot be compiled on the main thread with the synchronous method of compilation. And Webpack used the synchronous method of compilation for when they bundled up WebAssembly into a module. That caused the problem that these programs would not work in Chrome at all. So to get around that, I'll go through a few pieces at the bottom of how you might do the WebAssembly instantiation yourself if you didn't want to rely on Webpack to do that for you. I'm going to skip over a lot of this stuff. There's a lot of pieces to this that's really just kind of dealing with the memory pieces. I have attempted to define what each of these functions is doing on the website. If you go to the annotated version, there's a link that tries to break out each of them and go over them. But let's just slide down to bin code to JSON. There we go. We have get add message, get update message, get remove message, get all message. Right? So we have all of our bindings. The changes that we're going to need to make to get around that bug in Chrome, which I will say I believe is fixed now, but not, it's been like 2 weeks maybe. So I'm sorry I didn't update this. So we're going to remove the import statement to get around the Webpack piece of things. And instead, we're going to declare a global variable with the same name we were assigning to before, and a new exported property called booted that will just be a promise to say when we're done. Booted will be assigned to the promise of fetch of the file we created. Right? We know that's going to be the name of it. Then turn the response body into an array buffer. Then take that buffer and pass it to the WebAssembly globals instantiate method. So that's the first argument. The second argument is the import object, which we'll go over in just a moment. Once that happens, so this is the asynchronous method, so we can do this on the main thread if we want. Once we have that, we'll go ahead and assign Wasm to the module.instance.exports. So that'll just expose all of our exports to that same variable that we were depending on before. The import object is going to have this basic construction if you're using the Wasm bindgen piece. So it'll have the package name, so / your package name, not with any stuff after it. Each of the exported function names in the file above, and then a placeholder version with the same. And this will be empty versions of whatever it is. So you can actually move full Rust structs into the JS environment. In that situation, it would just be empty curly braces like an empty object. For this, it's going to be all functions, so we're just going to set it all to empty functions. Once we do that, then we'll be able to successfully compile that and use it. Now, while your server developer was developing the server, you weren't idle. Right? You actually built out the application as it should work with the information you had. So first, we have this app.ts file. So we have the renderer. I'm going to switch gears and work in TypeScript just because it's a little easier to do something slightly larger for me. So we have renderer and then our models that we're going to depend on. Just to start, we're going to, when the DOM content loads, we're going to create a new app, assign it to a global variable so it's just in memory. We have some mock to-dos that will just live globally that we can use to pretend that we have the service available. And then here's our actual app. So the app first is going to, in the constructor, register the events. That's going to be just the plus button for adding a new to-do to your to-do list. When you do that, it's going to go into this to-do function. We're going to get a little bit repetitive here, so I might gloss over some of this stuff. So we're going to get the input from the DOM. If we don't find it, we're going to show the user an error message. We're going to set the action to the variable, and then we're going to create a new to-do and add it to our property of to-dos. Right. Remove, we're going to do essentially the opposite. We're going to filter the list and make sure that that to-do is not in there with the ID. Marking a to-do, we'll get the state and update the to-do with the ID in the state. Right? And then render, we have a DOM element that's just a container. We'll empty that all out of stuff, and then we'll go to our renderer. Oh, sorry, then we'll split the list of to-dos up into complete and incomplete. And then we'll go to our renderer and actually pull those DOM nodes and put them into the container. So let's take a look at what the renderer looks like. So the main entry point here for a to-do list is going to be a list with a title, your actual to-do items, and then 2 callbacks, one for when it was removed and one for when it was changed, right? So we'll create a container for a single list. We'll set some attributes on it, give it the title with an H2, and then we will move into a couple other, move down a little bit. If the list doesn't exist or there's no elements in the list, we just have a dummy item so that it still takes up a little bit of space. So to-do item is going to be a div. It's going to have 3 elements in it, a checkbox, a actual action string, and then a remove button. So the checkbox is going to be a div. We're going to set the value to either the ballot checkbox or space, depending on the state of the complete Boolean. And then we're going to register the event listener, so when you click it, it changes from checked to unchecked. Right. The to-do action, so that's going to be the actual span that the text lives in. So it just kind of shoves text into a span. And then the remove button is going to be a button element with the ballot X as its text. Dummy element is just going to be one div that takes up the whole space that has the text you provide in there. So for us, it's going to say nothing here, I believe, is what I said. So yeah, nothing here. All right. The last piece in here is slightly different. I added it much later. So this show message takes in a string, and whether or not it's an error, it adds the message into a div on the main page, waits 3 seconds, and then destroys it. So it just sends a toast message out, essentially. All right. To do, this is really unused, actually, in the overall grand scheme of things, but it's nice for constructing our mocks. So ID, complete, and action. Main.css, I'm not going to really spend a ton of time on this. Lots of flexbox, because that's the way I like to do things. And there is animation for our toast. These keyframes here roll in. Those are kind of the 2 big pieces. Again, this is all available online if you want to dig further into how this stuff works. Or once I'm done, we can go through any questions you might have. Now our configuration files, so we have package.json. We're just going to be doing the same Webpack stuff. This time, we do need the TypeScript pieces. In our TypeScript config, no implicit any I have turned off. The reason being is that WebAssembly's global is not currently available, at least in VS Code. So this kind of helps me deal with fewer red squiggly lines. Now the Webpack config, it's going to, again, be super simple. The only additions to this, the only changes that have been made are the TypeScript additions. So adding the TypeScript loader and the TypeScript as a possible target or resolution thing. So now let's build something that's a little bit nicer to deal with than our raw Wasm module, right? So we have those bindings, but they all have Rust-based idiomatic things. If I want to use this in my network or in my app, I like it to look a little bit better. So I've created a network class. This is going to be essentially a service that the app will use to deal with any network communication. So this is going to do all of the wire stuff. So the 2 biggest pieces here are the request and the buffer to array. So the request is going to just take in the route, an essentially optional body as an array buffer, and then whether or not it's a post request. It's going to pass that stuff to fetch, and then if that's not OK, then we're just going to show, we're going to throw an error, which should get caught above, with the text that's in the body of that. In the event that it is OK, we'll return the array buffer out after passing it into buffer to array. So if we run up here, we can see this is where the response is going to go into the Wasm scope, get converted into JSON. We'll get that back as a string, right? And then pass that into json.parse and return that to whoever's calling it. So the other pieces are the individual activities, right? So to get to update a to-do item, we'll take in the to-do item. We'll send the values into the Wasm scope, get our array buffer back, and then return request with that data on it. So that's, again, going to go through here and resolve into a list of to-do items for us. So each of these is just going to provide us with a brand new list of to-do items in a promise. Right? So slightly better abstraction than all of the mess in the bindings file. All right, so when we incorporate it, we'll go ahead and bring that network service in at the top. This time, we're actually going to change from the DOM content loaded to the booted promise. Once that boots and we're ready to go, the DOM's most likely ready. It's going to take significantly longer currently. So I'll set that to the global variable just like before. And then in our actual app, in the constructor, instead of setting our mock to-dos to the value of the property to-dos, we're going to do http.get to-do list, right? So our network service is going to get the to-dos. When we get that promise back, we're going to throw that into our property of to-dos and then re-render the to-do lists. In the event that that errors, we're going to show the message that we were unable to do that. In each of these functions that we sort of touched on before, it's literally adding that same thing to them, except for there's a different error message, right? Or there's a success message if we got everything correctly. But it's going to add the to-do item. If we get all of the to-dos back, we update the to-dos in this .todos, and then we re-render. All right. So nothing really else has changed there. So then we can go ahead and build our application with Webpack. Here I'm using the locally installed node modules instead of a global one. Because we did that sort of hacky fetch piece, I do want to make sure that the bin code parse bg.wasm file gets into the dist folder. So when this request comes in, it's in the right place. But other than that, that is all it takes to get this working. Now, this is where you could clone and run the server that I built to act as the opposite side of this client application if you wanted to do that. If you come to this website, it's this link. If you prefer that, there is a build.sh to make your life a little easier. But let's take a look at it working right now anyway. So I deployed this to Heroku. So this is WebAssembly running on Heroku with a Rust server behind it that is dealing entirely on the wire with bin code. So let's just make sure that Heroku hasn't died because it's been a while. All right. Somebody's been adding to-do items to it. So I can mark these as complete. Can add a new task. There we go. So we've gone ahead and done that. And if we look at the developer tools, we can actually take a look at, let's see here. Here's a to-dos route. So this is our GET request. We look at the response. The response body is going to be this giant glob of bytes that it's attempting to turn into hypertext. So you can see that we have successfully made these requests just in bytes. So that is a more contrived example. I'd be happy to answer any questions that you guys have, but that sort of wraps up what I've prepared. Yeah. Shoot.
So we've established that we can do this.
Sure.
And certainly it's all right to do things just because they're fun and we learn a lot along the way. Is there a reason, a case where we should do this? Is there a case where this would be like a wise decision to implement this in this way?
Sure. Well, maybe not this, but WebAssembly is extremely performant. It provides near native speeds. So if you had an application that you were hoping to get Silverlight or Flash-based performance out of, you can get a significant bump from that here by using WebAssembly to sort of pick out the performance-heavy pieces of it. One of the major interest pieces for WebAssembly right now is game development, because you can actually develop like native games in WebAssembly. The ASM.js talk I was talking about earlier, he actually shows like a game from 2010 being played in a browser. And that we've come further than that. It's better than that now. So that's kind of the use case right now. Do you have a question? No? Sorry. Shoot.
Okay, so what are the drawbacks? So we have a download issue. There's going to be something.
Sure.
What is it?
So right now, the ergonomics, I think, is the biggest drawback. The Rust Wasm piece, there is a little bit of a bloat we have to deal with because it's so young. Hello World is somewhere around 200 kilobytes. Chrome's vision of a appropriately sized WebAssembly module was 4 kilobytes. So we've got some ways to go to get there. But those are the two biggest drawbacks, I would say. Yeah.
All right, another one.
Yeah.
Have you benchmarked anything that you've done here versus fully JavaScript? So,
No, I haven't personally, but I guarantee you there are a ton of people who have been doing that. I've seen somebody attempted to port Flash to WebAssembly successfully. It's been ported to ASM.js a couple of times. And there's a comparison of ASM.js versus WebAssembly in Flash rendering random stuff. So I'm sure it's out there. I can look for it. I don't know.
so can I. Did you do this with a company called Bitwise?
Yeah, I gave a draft version of this talk at the Rust meetup a couple of months ago just to try and prepare.
I thought it was familiar.
Yeah, makes sense. All right, I think the last call for questions. Is there a hand? No?
All right, I gotta ask you, what do you have running in production?
In WebAssembly, I don't have anything running in production.
Come on. Okay.
I don't have anything running in production. I have a couple of things that I have one thing, I guess, that I played around with when I was really getting started. I would not call this a production environment, however. So here is a WebAssembly serialization test, sort of how I got the idea for the talk contrived example. So here is a comparison of the server, which is just like a $10 droplet on DigitalOcean, compiling these and the times on those. And then this is the WebAssembly doing the same thing. This is a little bit of a smoke or a snake oil test because with all the Spectre stuff, you can't actually get performance timing in JavaScript anymore. So this is up to 2 milliseconds off, and that's a pretty big margin, right? But it's a fun example, right, of a place that it's working. I'm trying to think of like bigger things that I've heard of. I know that the people behind Ember.js are huge fans of Rust. Yehuda Katz, who maintains that, is also a huge Rust contributor. I believe they built some stuff into their Ember that is using WebAssembly currently for some diff performance stuff. So that's probably the closest I've heard of to production stuff.